Hello everyone, I'm Pratyush and I'll be discussing about LVDT experiment. This is the LVDT experiment kit that we will be demonstrating in this video. It contains a cathode ray oscilloscope or CRO, which will be used to measure the modulated output as VRMS or Vmax readings can be seen on the CRO. Then there is the LVDT setup main unit, which consists of a carrier source, a signal amplifier, a demodulator, 3.5-digit panel meter, and an IC regulated power. We also have the mechanical unit of the LVDT setup, which has provision for movement of the core. The soft iron core is coupled to a threaded rod that is moved by a thumb wheel arrangement, as can be seen here. Now let us understand the theory on which LVDT is based. Here we have a schematic diagram to explain this. LVDT is a linear displacement transducer. It consists of three coils, one primary coil and two secondary coils. A core is placed inside the coils. This core is made of a magnetic material, typically a soft iron. There exists a mechanical arrangement to move the core. An AC signal, called the carrier, is connected to the primary coil, which induces voltage in the secondary coils. When the core is at the center of the arrangement, the output signal is 0 if the coils, which are the secondary coils, are symmetrical. Once the core gets moved from the center, asymmetrically, flux gets induced in the secondary coils, due to which different voltages are induced. In this situation, a non-zero output voltage is observed. There is also a concept of residual voltage, which is the voltage due to incomplete magnetic or electric valence observed at the zero displacement position of the core. Considering that the LVDT is not getting loaded, the output that we get is EC multiplied by M1 minus M2 by LP, and the reading we get is in volts. Here M1 and M2 are mutual inductances between the primary and the secondary coils. LP is the self-inductance of the primary coil. EC is the carrier signal. Now in the demodulation process, the modulated signal E0 is multiplied by the carrier signal, and this is passed through a low pass filter. What we get is the demodulated signal, which we get in the millivolt range. From displacement value of -6 centimeter, we will start taking the readings. We will get the demodulated output on the 3.5-digit panel meter and the modulated output reading on the CRO. On changing the course location, we will obtain our further readings. From x equal to -1 centimeter value, we will observe non-linearity in readings as discussed later. After this, we will take a reading at x equal to 0 value of displacement. As the core reaches the center, we will take the residual voltage readings. When we reach displacement of +6 centimeter, we will take our final readings. On performing the experiment, we get the readings as shown here, based on which we have plotted the following graphs. Graphs have been plotted for both modulated as well as demodulated outputs. Here we see that as the displacement is kept near 0, the magnitude of modulated as well as demodulated output is very less. However, for distances away from the center, we see that the magnitude is larger. Now we come to the results and conclusion. For modulated output, we see that the calibration factor, which is delta E0 by delta x, is 0.26 volt per centimeter. For demodulated output, this calibration factor comes out to be 35.46 millivolt per centimeter. In case of modulated output, we see that linearity range is from -5 to -1 centimeter and from 1 to 5 centimeter. For demodulated output, the linearity range is from throughout -5 centimeter to 5 centimeter. Also, there is a presence of a residual voltage of 0.12 volts in modulated output and -7.9 millivolts in demodulated output. Finally, we find that the graphs obtained are fairly linear over a large range, as it was expected from the theory. Now I will present an innovative idea using LVDT. My idea is to measure velocity of stream based on the displacement measured by LVDT. This animation shows how exactly I want to make use of LVDT for this purpose. Based on the velocity of the stream, water will get filled inside the tube, which will move the piston-like arrangement. This will eventually displace the core of the LVDT. Now, this displacement can be measured. After this, since we know the value of h, we can use this formula, velocity of stream equal to CV root 2gh, which comes from Bernoulli's principle, to calculate the velocity of stream. Thank you for watching this video.